Welcome back, guys. In this video, what I want to do is talk about a fundamental concept, two actual questions that form probably around the basis of linear algebra. And this involves the existence and uniqueness of solutions. So when we're solving a set of linear equations or any sort of system as such, we have two questions we could ask, and that is, one, does a solution actually exist? And if so, is this solution unique? And in order to answer these questions, we have to take a look at what we would call the solution space. So as we saw in the last video, we had a system where we had x plus 2y equals 3, and then I just went ahead and drew the line, and then 4x plus 5y equals 6, and I'm going to draw that as well. And we found that this system had a single solution, and that is at the point minus 1, 2. So xy equals minus 1, 2. That is the solution. So we have these two lines and they're intersecting at a point. And this holds true to higher dimensions as well. If in 4 dimensions we have 4 what we would call hyperplanes, or in 3 dimensions 3 planes, if they're all intersecting, you can get one single point where all the planes intersect. And there are lots of other possibilities too, and that's kind of what we're going to talk about today. So we saw that when we're solving the system of equations, we got a single point. So yes, in answer to the first question, does a solution exist? We say yes, a solution does exist. And with response to the second question, is a solution unique? We're going to say yes as well. It is unique because there is only one of them. So this one actually satisfies both the existence and uniqueness question of there being a solution to this set of linear equations. So now what I'd like to do is take a look at another set of equations. The first equation is the same as before, x plus 2y equals 3. But now we, instead of 4x plus 5y equals 6, we're going to have 4x plus 8y equals 6. And I'd like you guys to kind of think about this. You can pause the video if you'd like and think about what may actually happen in this case. What is different and what do you think could be the possibility? And you can think about this mathematically, but you can also think about this graphically as well. What happens when you try to solve this system? So what I'm going to do is I'm going to go ahead and write this in matrix form. So this is the way we have it. 1, 2 augmented with 3, and then 4, 8 augmented with 6. And what I'm going to do is I'm going to take 4 times the first row and subtract it from the second row. So the way I'm going to write this is R2 star is R2 minus 4R1. And the star is just basically saying, like, I'm changing it. This is its new value after I perform this transformation. So once I do that, we're going to take 4 minus 4 times 1 is 0. 8 minus 4 times 2 is also 0. And then 6 minus 4 times 3, that's 6 minus 12, that's going to be minus 6. So if I draw that out, I'm going to have 1, 2, 3, 0, 0, and minus 6. And you're probably looking at this and being like, well, what the heck? Like, what does that mean? And this right here is bad, and I'll explain why this is bad. If you remember, the way we interpreted these and the way we came about these is we were literally writing equations. We were writing, these are the coefficients of the equation. The one on the left is the coefficient of x. The one on the right is the coefficient of y, and then the one on the far right of the bar is the thing on the other side of the equation, what it's equal to. So what this is basically saying is like 0x plus 0y equals minus 6 if you interpret that last equation. In other words, that's like saying 0 equals minus 6. This forms what I would call an inconsistency. Like, how is it possible that 0 as an entity is equal to 6 as an entity? And that's actually really bad, and that basically tells us that there is no solution, because there are no x's and y's that, when multiplied by 0, can get us minus 6. So we like to call this an inconsistent system. And in order to answer a question, does a solution exist, we say no, it does not. And of course, we could try to answer the second question, is it unique? But since the solution doesn't even exist at all, we can't even answer that question. It just kind of is undefined. So when we ask, is it unique, I just kind of say not applicable. And the way this would look graphically is if I draw my axes and plot the first line, which goes through like so, and I plot the second line, which is actually going to be right below it if you work it out. There it is. And both of these lines are actually parallel, so they form parallel lines that never intersect. And actually, that's the definition of parallel lines. They're lines that never touch. So in that way, we will say there is no solution to this problem, and a sad face because we cannot solve this. There's never a way we can solve this. So that's a case where a solution does not exist and it can't be unique, and you can have these systems. In fact, most of the time when you make up a bunch of coefficients, there'll be a solution, but in certain cases there won't be any solutions, and it kind of sucks. So I bet you guys can think where I'm going next. What is the third case we can have? So go ahead and erase everything. And I'm going to start with a similar set of equations to the last one, but they're going to be a little bit different. So I'm still x plus 2y equals 3, but instead of 4x plus 8y equals 6, I'm going to do 4x plus 8y equals 12. And I kind of want you guys to stop the video and take a moment to think about what may happen. What could this cause to happen, and what's different about the system? How would it look graphically, and what would we come to a conclusion about the solutions to the system based on this? So in this case, if I draw it out, or write it out, sorry, as a matrix, I will write 1, 2 augmented with 3 and 4, 8 augmented with 12. And like before, is what I'm going to do is take 4 times the first equation and subtract that from the second equation. In other words, R2 star is going to equal R2 minus 4 times R1, which gives us the following system. 1, 2, 3, and then all zeros, because 4 minus 4 times 1 is 0, 8 minus 2 times 4 is 0, and 12 minus 4 times 3 is 0. And you're probably looking at this and going, huh? Like, what is this? Like, why is 0? Like, what does this tell us? And it actually, really, it doesn't tell us anything, because if we write this, once again, thinking about this as a system of equations, and that's one of the things that, kind of as a sidebar, it's good to kind of have these multiple viewpoints on the way to see these things. It's good to see these graphically. It's also good to think about them computationally as actual equations. And it's also good to kind of build up an intuition of how matrices sort of work on their own, as if they're kind of a physical object. But kind of shifting our lens from matrix land back to equation land, this is kind of like saying 0x plus 0y equals 0. Or in other words, 0 equals 0. And that's kind of like a duh, kind of obvious sort of thing. Like, duh, of course 0 equals 0. Like, it wouldn't be, it wouldn't be 0 otherwise. Like, 0 can't change. It's always 0. But this actually talks a little bit more about what's going on under the hood in this system. And it's because we're kind of removing a constraint. This last line in the matrix, that second row, that's not really telling us any new information. It's basically telling us 0 equals 0. And any combination of x and y are going to cause that last row to be true. And what that's basically done is we have gotten rid of a constraint to our system, and we have basically added another degree of freedom back in. So if I graph this, x plus 2y equals 3, I can plot the line like so, and then plotting 4x plus 8y equals 12, it's basically the same line. They're both overlaid on top of each other. They're just different ways of writing the same thing. And what this is basically telling us is any point on this line, because these two are really the same line, is a solution to this equation. And what that means is that there's a whole line of solutions, and in other words, there's infinitely many of them, because there are infinitely many x's I could pick on this line. It's a continuous line. In other words, I would say that there are infinitely many solutions. So when we ask, does a solution exist? Yes, it definitely does. You can tell me any point on this line and I will say, yes, that's a solution to this. And then of course asking, is it unique? The answer to that is not at all. It is not a unique solution. And this kind of gets, and actually even further, not only is it not unique, but there are infinitely many solutions to this system of equations. There are infinitely many points that satisfy this system. And there are many ways you could talk about this system. There are many terms for it. But the intuition I want you to have is every time that there's not a unique solution, there are going to be infinitely many of them. And this is true just in linear systems. In other systems, it can be like, oh, there are two, there are 2 points, or there are 2 solutions, or 5, or some arbitrary number. But in linear algebra, in the land of linear transformations and such, if there is more than one solution, there are automatically an infinite number of them. And that's just kind of a property of linear systems and linear algebra, and we'll go into more detail about that later. But for now, keep in mind these 2 questions, existence and uniqueness. Does a solution exist? Yes or no? And if so, is that solution unique? All right, I will see you guys next time.